Yeah, this will be a a talk devoted to software and creating the software. I'm sure I was put last because throughout my career I have always ended my talks early. I'm a little nervous today. It's going to be tough, so we'll do my best. I'm going to give some background, which is, I hope, enough for you to sort of understand the algorithm we're using. It helps to follow Patrick. And then I want to talk a little bit about some computational issues associated with implementing this operator splitting method that we're using. And then after the conclusions, I have some results. So that's one of the things I can use to bail myself out if I'm not going to make it on time. So I'm going to ask you to kind of look at these slides as you would look at Impressionist art. So you're not looking for the Big Dipper there, the Southern Cross. It's just impressionistic, and that's what we're going to do with these slides. So there's going to be sort of an art theme, and we'll just continue that through. So let me get the citations out of the way early, too, so that I'm going to look at some problem instances that most of you, maybe none of you, are familiar with. So there's some citations for those, and there's some algorithms. I'm going to go to the next slide and just get the citations up here. So this first paper concerns a problem instance from stochastic programming. Let's see, this is the mothership. No, yes, the mothership paper, and then
actually was written
the life raft paper. I don't know what. Yeah. And then that concerns this ALP1 problem. It's a paper about a problem instance in stochastic programming. This is also a paper about a problem instance in stochastic programming. This is a paper about a well-known algorithm. This will be the fourth talk that's mentioned progressive hedging. But we'll come at it in a little bit different way. And then this concerns another problem instance that we're going to study in stochastic programming. And this also concerns a problem instance in stochastic programming. So let me kind of set the framework. I'm wearing my Pyomo shirt. John Paul and I and others, John Cirola, who's here at the workshop, work on software that's a general purpose modeling language for optimization. It's an algebraic modeling language. If you're familiar with AMPL or GAMS or AIMMS, it's vaguely reminiscent of those things. It's probably more reminiscent of Pulp if you know what that is. But it's an algebraic modeling language in Python. And it has a lot of features. You can write down differential equations for your constraints. It'll automatically discretize them, et cetera, et cetera. So it's a full-featured language. And we have in it an implementation of progressive hedging. So that kind of colors our work. Modelers, graduate students, regular people in industry, et cetera, make models, and then they feed it to the software. And whatever they did in their model, that's what comes to us. So and then that will affect kind of how we design this software that I'm going to describe. But before that, let me get some notation going. So what Jonathan did was took sort of the standard objects of stochastic programming and set them up for use in an operator splitting algorithm. So these concepts are well known to people. The exact notation is slightly different than normal. Again, I hope for most of you, though, this should, well, after this slide's going to be, but after this slide, it should look like things you're used to. This slide is sort of the key slide, though. We're going to, for these stochastic programming problems, the dirty secret is almost every talk you attend does not consider a stochastic programming problem. They consider what would be a subproblem for a stochastic programming problem. They make it a deterministic problem with scenarios that are provided for data. We attach probabilities to the scenarios, and we organize the scenarios in a tree. But in most applications, we took a high-dimensional probabilistic space and sampled from it somehow to get a deterministic problem. And we mostly work on the deterministic problem. But it's important to remember that if you're really interested in the original stochastic problem, this will be a subproblem to that problem. And that's going to come back to haunt us a little bit later. But right now, let's just set up the data, which you don't have to memorize this at all. But suffice it to say, you need some data processing, some notation to deal with the scenario tree. So these are the input data. And in the end, each scenario is a full set of problem data. So think about a linear program. So all the problem data for a linear program with an attached probability. Then these decision processes go in stages. So we may organize the data in stages. If you like to use the word filtration, you can use that and say there's a filtration and we need to have it so that we take this filtration and organize it into a tree, discretized tree. For those of you who have worked on various kinds of stochastic optimization under uncertainty, these methods are designed for relatively few stages, 3, 4, 5, 6, and relatively high dimension in the decision variables, millions or so. So what we're going to do is set up the decision variables, and we're going to treat the final stage decision variables specially in a minute, but for now we just have all these decision variables in a space, and in order to make our work look like progressive hedging, we're going to have a special inner product operator that throws in the probability. So this is the probability attached to the scenario, and otherwise it's like an inner product, but it will make everything work well, both for our software and for making things look like progressive hedging. But again, for you, the main thing to know is we have a space with this somewhat special inner product. And then the other thing we want to do is lift. And so we take, since in general, of course, this is a tree, so we're going to make certain decisions now and then certain decisions in the future. And in order to make the sort of notation simpler, we replicate every variable for decisions to make now into every scenario. Okay? And that's not as unnatural as it sounds. So every scenario has the full set of variables. So for every possible future, we have a full set of variables. And we have some notation to make that happen, which we no need to dwell on. So, I should say, Jonathan showed this grid, though, yesterday. So if you were really paying attention, have a great memory, he put a slide up with this on it. So the other thing we need is an operator to make the notation work. And this is sort of important to thinking about optimization under uncertainty. The final stages are special. So in the final stages, you're going to know everything you're going to know, and your decisions at that time can depend entirely on the scenario. At all previous stages, your decisions can only depend on the information you know up until then. So we need to, on everything other than the last stage, we need to perform some operations to make them non-anticipative. And Jonathan was a little harsh about that word, you might remember yesterday, but really it's the secret handshake of people in stochastic programming. You should be able to say that easily and without complaining. So, so non-anticipativity is very important to enforce. And so we have this operator to take our decisions and kind of ignore the final stage because it's special. But that's all this is data processing to do that. But we're starting to get into land where you might be familiar with. These Z's are going to be kind of what you think they might be. So we have an operator to get us from X's to Z's. So the leaf node decisions don't need to be projected, but all the other decisions do need to be projected. So we're going to have this M that gets us from X to Z. And basically this operator, if you're a computer programmer, this operator just drops the last stage decisions. Now we're getting into the stochastic programming part of it. We're going to need a linear subspace that is the subspace of non-anticipative solutions. And this is just a way to write it. And what this says is that the decisions up to a node in the tree have to be the same. Right? So you can only use the information you have up till now. Now we're ready to write down the standard, and this will be the third or fourth time we've had a stochastic program written down, or optimization understood, but now we have a little bit different notation than before, so let's look at it for a second. So what we're saying is that we need to minimize the expectation, and it's easy to add conditional value at risk as an expectation if you want to do that, but just take the expectation for now. And we're going to just sort of roll into this, all the constraints and say that it takes on the value infinity if it's not feasible with respect to constraints. And the only constraint we're going to explicitly note here is non-anticipativity. Right? So remember, this operator took away the leaf nodes because they don't need to be non-anticipative. Said you have to be non-anticipative. So on this slide, this is where we're getting into ADMM land. The idea is that we can write this down in such a way that, and that's why I wrote deconstruction, although progressive hedging wasn't written, if you read the paper, the word letters A, D, and M are all in there, but not together and not capitalized. So it wasn't intended to be that way, but you can deconstruct it to be that way. And so here's how you do that. F is this function, and G is this function that indicates you're non-anticipative. And this projection onto that space is how that paper is written. And so it is similar to ADMM. And when you look at progressive hedging, as you saw it a couple times yesterday, it looks like that. So what we're going to do now, though, is switched operator splitting, and we're going to turn this into an n-way decomposition. So every scenario, so we have n scenarios, we have n possible futures that provide all the data for the optimization problem. We're going to break it up that way. Okay? And then this is all Jonathan speak for, we're getting ready to do operator splitting. So, but if you're a stochastic programmer, all we're saying is we're going to break it up by scenario. And if you're going to do this slide is for you folks more than for me, and this is where I'm going to get off the boat right here. So if you're going to do operator splitting, here's the story. Going back, sorry, I'll go back a slide just to see where we are. So Z and H0. So we're going to require that these are the projected things are projected onto the space of non-anticipative solutions. We're going to have the inner product. We're going to be able to pick out the parts of Z that need to be non-anticipative. F is split by the projected variables and then the variables that don't need to be projected. And everything's scaled by the probability. So this minimizing over the last stage variables is what we're trying to avoid having proximal terms attached to things we don't need to project. Now, that's it. I'm done setting things up. Now we're just going to put the algorithm up there without enough setup. But if you saw progressive hedging, this looks a lot like it, except it looks like operator splitting too. So let me sort of explain the algorithm, at least from a computational perspective. And so we're going to iterate forever, right? And in practice, if I do get to the results, we of course terminate often on just number of iterations. We've just spent as much time, bearing in mind that this problem itself is often a subproblem. So we may just want to solve for a while. There are other convergence criteria that I'll get to in a minute. Anyway, the main thing is, and this looks just like, or it's intentionally looks a lot like progressive hedging, and it looks a lot like operator splitting too. We're going to solve every scenario separately. And perhaps more importantly, we're only going to do a subset, just like in the previous talk. So we're not necessarily going to solve every subproblem. We're only going to solve some of them. And then when we get enough of them back, think 100 or 20 or some number like that, we're going to then do these updates. We're going to project, we're going to find a projection, and we're going to find a step size, and we're going to project onto the space of non-anticipative solutions, and we're also going to do projections in the dual space as well. We're going to decide that we must have converged if that's what we really want to do, if these guys get to be close to 0. Okay, so checking that for convergence, if you were going to wait for convergence, that's what you would do. So how am I for time? Okay, so I'll come back to this if I may need to, but maybe you get the feel. Again, the highlights are we're going to solve for each scenario. The subproblems, unlike other talks, are not particularly easy. Although so if you saw the talk yesterday, they could be MIPS. In the case of today's talk, though, they're going to be convex. They're going to be linear programs. They're not that hard either. They're pretty easy. They will be quadratic once you put the term on, yeah. So some of the issues now on making this work is how many workers are you going to have to solve these subproblems? So on the experiments that I'll show you, there are 50 workers. How many threads per worker? There are 2 threads per worker. But these problems, the problems I'm going to look at, the individual scenarios are not, they're small LPs. They have 200, 300 variable LPs. So they solve very quickly. There's a parameter rho that we just set to 1 for these experiments. There's a parameter gamma that we just set to 1, so it's not important. The buffer length is an important topic. Let me go back. And that's something we're studying right now. How many scenarios do you want to wait for? So you send them all out and you wait till some come back. How many should some be? How many of them should that be? And then what's going to cause you to quit? Okay, so it turns out that in the experiments, most of the experiments I'm going to describe, not all of them, it terminates on iterations. So, oops. So before showing any results, let me talk about some issues. One of the toughest issues is the termination criteria. What do you want? Do you want non-anticipativity? Is that good enough? In a lot of the work we do, this makes Jonathan unhappy, but for myself and John Paul, when we get a non-anticipative solution, yeah, we're out of here, quitting time. So if we could just get them to converge to the point where they're non-anticipative, we would quit. But you can do better than that by waiting until they've converged more in both primal and dual space, and you will get better solutions that way. So if you wait longer, you'll get better solutions. And the criteria of waiting until you don't have any projection left to do, if you could wait all the way till there's 0, but you can't wait that long, and that's the trouble. So the other trouble we have, and this is important for all of these operator splitting methods, but particularly this one, is this. And maybe I should back up a second. I spent a lot of time working on generating scenarios, working with Roger Wetz, who's worked a lot on stochastic programming. And we worked almost entirely on mixed integer programs. And one day he said to me, not using these words, but one day he said to me, hey, how come we never do any continuous functions? You know, they're a lot of fun, and convex functions are especially fun. And I said, not using these words, fun for whom? Because the trouble with convex functions is, and continuous functions is, it's really difficult to exhibit a solution with the actual numbers in it, the vector, the x, that's the solution that's non-anticipative, if anyone can hand you any crazy model they want to. So if you wait until it's almost converged and almost all the scenarios are the same, this z thing you've got may not be feasible for any scenario. Let me make that clear, because I think that comes up in other contexts. So the trouble for us is we need to actually spit out a solution and say, here it is, the numbers, the actual vector. Not the objective function value, nobody cares about that. What they care about are the numbers in the vector. And they're going to use it in scripts later, so it's not good if it's infeasible. So that's the trouble. I mean, so if this z projection is a projection, and it might not be feasible for any scenario. So then with MIPS, or with pure integer problems, right, it's either 0 or 1, and it's not so bad to be feasible. But for these problems, can be much harder to get your hands on the solution. So that's one of the things we work on. You can imagine, and maybe other people have better ideas. So one of the things you can do is look at a scenario solution, because it's at least feasible for that scenario, and see if it happens to be feasible for the other scenarios, or various other things to do to try to find a feasible solution. So we're working on termination criteria, how to exhibit this actual solution, and then the length of the buffer for this asynchronous computing. So I'll give the conclusions, then I'll show some pictures, some results until I'm stopped. So we have an implementation in PySP, and it's asynchronous, or sort of quasi-asynchronous. It waits for a buffer. It could wait for one solution, but that's really foolish. So it waits for some number of solutions to come in. It outperforms pH on many instances, but the asynchronousness is what's really going to be important, I think, in the long run. So we're working on computational experiments, and the most important thing, and we've talked about this a couple of times already in this meeting, is during today's talk and in the results I'm going to show you, the subproblems are a single scenario. But that really isn't a good idea. A much better idea is to take multiple scenarios and treat them as sort of a super scenario. But I won't be talking about that right now. So it does this almost all the time, which is quite pleasant. I mean, apart from this x hat problem, it's not, it doesn't converge monotonically. So this is the UV norm, right? So if you just look at the projection vectors, are they getting to be no projection needed, right? Are they getting down to fully converged? And so if you just look at that norm, and I had to cut off the first iteration because it's a couple hundred. So if you start here, it comes down fast, and it really by 20, it's done most of what it's going to do, although the x hat solution quality you can get if you wait to 100 is substantially better than here. So this picture is slightly misleading in that sense, but you do get fast convergence. And this is a very typical picture. So let me show you, well, these are hard to read. There's a message here. These are too hard to read, really. But we're trying to look at the objective function, and we're trying to compare it to time, and maybe that's the main message. So progressive hedging is set to terminate really quickly on the variables being close to each other, and we let asynchronous kind of run. So those are the progressive hedging objective function values. They aren't very good, but it gets done really fast. And then we let the asynchronous thing run, and sometimes it can be even faster, and with better quality, but with other settings, it's faster, but with not quite as good a quality, et cetera. So these are the kind of experiments we're doing. Here's another one with the buffer length. This is for a very small problem, the APL1P problem. It's very small. And you can sort of see there is perhaps a best buffer length. These are solution quality and time. Let me show one more set of experiments, and then I will wrap it up. So these are sort of the interest of full disclosure. Solving these problems without bundling the scenarios is not a good way to solve them. A better way to solve them is to bundle all the scenarios and hand the whole thing to Cplex. So it's much faster. So that's this line that says EF that takes 70 some odd seconds and gets the best answer. That's the right way to solve these. So, but we're doing this to study the algorithms. If you have 100,000 scenarios, then you can't solve it that way. You have to solve it with even at 10,000 scenarios. So these experiments are with 500 scenarios. With 10,000 scenarios, you can't solve it directly. You have to use decomposition. But anyway, the thing I want to talk about here that we're working on is asynchronous progressive hedging. This is the SSN problem. It says, well, anyway, this is SSN. So it's a bigger problem. But these subproblems only have a couple hundred variables, 500 scenarios. And the time to solve is much longer with asynchronous projective hedging, but they're pretty good quality solutions. Progressive hedging doesn't do well on these with individual scenarios. The thing that we're studying right now, though, mostly is what sort of buffer length should we have for asynchronous progressive hedging? Sort of how does that relate to the problem size? Or is there any rule we can use to figure out how big the buffer should be?
But it is faster than
Synchronous progressive hedging.
Yes.
Yes. Which slides do you want to look at? Mine? Patrick's? I'm trying to get my slides up so I can angle for applause and shut it down here, but I might have to just go with these slides and call it good enough. So, all right. Thank you.